All right. Hello, everyone. So, kicking off Unit 4 here, we're going to start with Chapter 22, and that is going to be focusing on amines. Amines are a functional group that we've talked about a lot, kind of mixed in with other functional groups, but we have yet to dedicate any time exclusively to amines. So that's what we're going to be doing. But good news is that we are going to be pulling a lot on stuff that we've already learned. There's not as much new material here as we're used to when we get introduced to a functional group. So first of all, introduction. One of the big parts of every introduction would be nomenclature. Before we get to that, though, there's actually this way that we classify amines. Okay, so the simplest possible amine that you can have is just ammonia, where the nitrogen is bound to 4 different hydrogens. Okay, as we increase in complexity there, let's say that there's 1 alkyl group on there, that would be considered a primary amine. What about when 2 alkyl groups are bound to the nitrogen? You guessed it, a secondary amine. And then when 3 nitrogens are bound, that would be a tertiary amine. And there's actually even an instance where we have 4, oh, that one was bad. 4 alkyl groups bound to the nitrogen, which would then give it a positive charge. And this would be called a quaternary amine, also known as an, there's got to be 2 M's, ammonium salt. Okay, so just keep this in mind. We've seen amines play 2 major roles. One of the first things we saw an amine do back all the way in first semester, acids, bases, we learned that amines are actually pretty moderately decent bases. They're not crazy, crazy great bases, but they're not terrible bases by any means. And so nitrogen can, with its lone pair, accept a proton, thus acting as a base. And thus creating your, again, ammonium salt here, or quaternary amine. The other thing that we see nitrogen doing a lot, again, because of its lone pair, is acting as a nucleophile, in this case, with an alkyl halide in an SN2 type reaction, okay? This is because nitrogen has that lone pair, right? It's also relatively electronegative. So there's this high region of electron density that sits on that nitrogen. It is by no means as sort of good as a nucleophile as, oxygen in certain cases, are certainly not, right, as the amide ion where you have that negative charge. But even as a neutral species, it can behave as a nucleophile. Moderate nucleophile can behave as a base, moderate base. All right, so nomenclature. Basically, with an amine, guess what the ending is? Amine, okay? So I don't know why the books sort of sets it up like this. It's similar to alcohols, but instead of the "ol" suffix, you use an amine suffix. That's how all of our functional groups have gone, right? For each functional group, there's a unique suffix associated with it. In this case, that suffix is the amine suffix, okay? One thing I want to warn you about is if you notice down here, we got dashes and wedges going on, which means that this molecule here has RS stereochemistry associated with it. This is something that I've kind of been procrastinating on reviewing because I know it's painful for everybody, this sort of stereochemistry, how we deal with chiral centers, but it is something that's going to be on the ACS exam. So we need to be prepared to designate RS stereoisomers on the ACS exam, which is why I'm taking this opportunity, our last set of new nomenclatures, to make sure that we're going to practice this. So just be prepared. You are going to have to use RS stereochemistry designations on the quiz that's after this. I've linked to the lecture slides as well as the lecture videos that covers that. So if it's been a while, make sure to review that. I'm not going to spend time reviewing it here, but I posted all the information as to how you can go about reviewing it, but yes. All right. So first of all, what are we going to do? We're going to number our parent chain, right? Since in this case, that amine group is our highest priority group, we're going to start numbering in such a way that gives that the lowest possible number. Stereochemistry wise, this carbon right here is an R stereochemistry, as is this carbon right here. Again, if you can't convince yourself of this, please go back and review those old videos, because that's going to be an important part of this this lecture, basically, this quiz. Okay, so then we designate that as 2R and then 4R, right? That goes out front, that stereochemical designation, just like if it was an alkene, we would use EZ. For chiral centers, we use RS. In this case, they're both R. So 4, 6, those two positions have methyl groups on there. All right, so here's one methyl group, here's one methyl group. That's how I have my 4,6-dimethyl. And then 2 heptanamine, right? So I have the AN heptanamine, indicating that it doesn't have any double bonds in there. And then I have my suffix amine on the end. Okay, so that's how we go for nomenclature of amines. Amines have been around for very long time in the history of organic chemistry. And so what you'll often see is what would be the common name, and they're actually kind of IUPAC accepted as well, but they're not really systematic in the same way that you were used to. Especially, well, for primary amines specifically, you can use ethylamine, right? That just means that there's an ethyl attached to that amine, as opposed to the systematic IUPAC, which would be ethanamine. Isopropyl amine, right? You have a primary amine attached to an isopropyl group. The IUPAC name would be 2-propanamine. Cyclohexylamine, right? Again, you have your primary amine attached to a cyclohexyl group. This would be as opposed to cyclohexanamine. Remember, we don't even have to bother to put the one out front, because when it's a ring, we assume that we're going to start numbering from where that functional group is. So these are IUPAC accepted. However, they're not like systematic in the same way. So I'm going to call these common names, and this is the IUPAC names. Bottom line is I want to avoid confusion. So what I'm looking for are these systematic IUPAC names. The reason why I'm bringing up the common names are because A, they're not that difficult, and B, should you stumble upon one on the ACS exam, you won't deer in the headlights be like, I have no idea what's going on here. Okay, but what I'm really looking for is for you to be able to build these names systematically. So yeah, the IUPAC is the one that I'm going to quiz on. All right, so now we got to bust out our handy dandy functional group priority chart. This thing has gotten large and terrifying throughout the semester. Amines actually sit pretty much at the very end there, right? So below thiols, alcohols, certainly below all those carboxylic acid derivatives. The good thing about amines is there's not anything too terribly weird going on. Again, the suffix is just amine. And if it's a prefix, if it's not the highest priority group, the prefix would be amino. All right, so fortunately not too terribly hard to remember. So then if we had something like this, how do we go about naming it? Well, we have these two functional groups, an alcohol group and an amine group. The alcohol is the higher priority group. So how do we start numbering? We start numbering from the higher priority group. And so this would be 4-amino, right? Now it becomes a prefix, 1-butanol. All right, likewise here, remember this all by itself is a very special parent chain benzoic acid. And I have an amine in what would be the para position. Whoa. And so this is para-amino benzoic acid. Okay, so just be prepared for when it's not going to be the lowest priority, or when it's not going to be the highest priority group. That suffix, or I'm sorry, that prefix that we use is amino. Remember that when we're talking about benzene derivatives, when there's an amine group on benzene, that has its own special name, aniline, and we treat that as if it was a parent chain. So when there's another substituent on there, that becomes metachloroaniline. If there's, remember, you can only use the ortho, meta, para designations when there's two substitutes. So when there's more than that, we just use the numbering scheme. In this case, that aniline, that amino group always gets 1, 2, 3, 4, 5. And so this is 5-ethyl 2-fluoroaniline. So just remember, when we're talking about when an amine group is attached to benzene, it becomes a whole different parent chain. Okay, what about when we have primary, we talked about primary amines, what about tertiary, secondary, and tertiary amines? Again, there is a common nomenclature scheme that you can use where you just start stacking them up with the YL endings. So in this case, in alphabetical order, we have ethyl, methyl, propylamine, diethylamine, trimethylamine. Okay, notice how these are just having those sort of like treating those alkyl groups as if they were substituents on there. Again, these are IUPAC accepted, but I consider these to be more common names. I want to make sure you guys can build the most complicated amine that I'm going to give you, which is again this IUPAC system. So how do we do that? So when we have a primary or secondary amine, secondary or tertiary amine, again, to first approximation, the name of the game is just like it was before, right? You're going to number your parent chain such that it contains all the different functional groups that this molecule has, and it gives the highest priority group, in this case, the amine group, the lowest number possible, right? So here I'm going to number from left to right. But what do I do about these two carbons on the nitrogen and this carbon on the nitrogen, right? This is a tertiary amine. So I have to account for those carbons as well, right? Well, so I guess let's first assume that they weren't there. How would that look, right? So these are gone. These are just, let's say this is H2. Well, this would be, of course, I got to account for those two chlorines, but this would be 2,2-dichloro, 3-hexanamine, right? But now that would be if it was primary. So again, how do I account for the fact that I have these two alkyl groups coming off of there? Remember, every time you're doing nomenclature, your goal is to account for all carbons, all atoms that are in that molecule. And we do that by, instead of giving these alkyl groups a number like they would normally be given, we give them an N. Okay, so this is actually, hopefully this rings a bell because we've already done this with amides. But this is now with amines. So we have, well, so first of all, again, this stereochemical designation is going to be important. You guys need to review this. If you need practice, come to office hours. There's a ton of lecture videos and content out there that I've already produced that explains it really well. So I don't want to waste time here. But the stereochemistry designation at carbon 3 would be S. I have my 2,2-dichloro. Now I'm going to account for those groups, those alkyl groups on the nitrogen. N-ethyl, N-methyl, right? Here is my N-methyl group. Here is my N-ethyl group. Okay, so if it was a carbon, they would get a number, but it's not on a carbon, it's on a nitrogen. So you're just going to put that. Notice how it's still in alphabetical order. I go chloro, ethyl, methyl, just like I would if they were on carbons. Okay. And then 3-hexanamine, right? So you got to indicate the position of the amine group. And then the N indicates that those alkyl groups are on the amine group. One thing I want to point out is, let's do another sort of similar example. What if these were, instead of being chloro groups, they were methyl groups as well. Okay, how do I list all those together? I'd still have the 3s, got to indicate that stereochemistry. And then this would be N, well, it would actually first be N-ethyl, and then N3, oh, no, not 3, sorry, N2,2-trimethyl. Okay, so the N, if you have multiple, in this case, methyl groups, the N actually goes before the numbers, but notice how I'm listing it just as if it was 2, 3, 4 trimethyl or whatever it would be. I'm still just putting those numbers separated by commas in front of trimethyl. In this case, instead of a number, it's an N. And again, just the important takeaway that I'm trying to get to here is that the N actually comes before the numbers do. So this would be N22-trimethyl 3-hexanamine. And of course, you can also always do just like normal hex and 3-amine. That's perfectly acceptable too. All right, other random crap about amines that we need to go over. So first of all, the nitrogen has that lone pair. That lone pair lives in an sp3 orbital because this nitrogen, in the case of amines, are sp3 hybridized. Okay, all the bond angles are approximately that 109.5. Remember that that lone pair takes up a bit more room, so that shrinks these bond angles down to about 108, whatever. The thing about amines that's kind of crazy that we haven't talked about and is pretty interesting is, let's say we had a tertiary amine that was bound to 3 different alkyl groups, right? This is a methyl, this is an ethyl, this is a propyl, right? That lone pair is yet another group, right? So you could say that this nitrogen is a chiral center. It has a mirror image that is non-superimposable. So it's really tempting to think about this as being chiral, right? And so, like, strictly speaking, if you could freeze time, it would indeed be. But it turns out that amines are not optically active. So it means that they're not chiral. So how the heck does that work? Well, it turns out that amines actually intraconvert, kind of, you know, like flip back and forth, back and forth. This lone pair actually switches sides rapidly, okay? So it goes from being your, let's just say that this is the S stereochemistry if we went through and designated groups, but it intraconverts with that R form as well. Okay, so it goes through this trigonal planar intermediate. There is, of course, an energy barrier to do so, but it is not that large. So at room temperature, these are rapidly interconverting between. Okay, so there is no, I mean, it's actually good news for y'all as organic chemistry students. It's also super interesting. But again, good news for you as organic chemistry students is nitrogen's never going to be a chiral center because it actually flips back and forth between the 2 conformations. Other properties of amines. So first of all, again, this rule of thumb, similar to alcohols, if you have fewer than 5 carbons typically soluble in water, that's the same rule we had with alcohols. If you have more than 5 carbons, you're typically insoluble in water. Not only that, but let's compare this sort of hydrocarbon group to an amine group to an alcohol group. What's going to be the difference between those, right? So one of the big forces that account for the intramolecular interactions in amines are hydrogen bonding. Remember, there's 2 big things that sort of influence how strong hydrogen bonding was. One is how many hydrogen bonds you can make. And this is something that actually back, I don't remember, first semester or the beginning of this semester, people sort of got confused about, well, there's 2 hydrogens here. So doesn't that make it better than an alcohol group that only has 1 hydrogen? Well, yeah, but it only has 1 lone pair compared to an alcohol group that has 2 lone pairs. So although it has 2 donors, it only has 1 acceptor. So that's kind of a wash when we're comparing these. The biggest thing is the difference in electronegativity. That's something that influences how strong a hydrogen bond is. So a hydrogen bond is not as strong as an oxygen hydrogen bond. Holy cow. A lot of elements being spit here. So the boiling point of propane is -42 because there's no hydrogen bonding going on. When we get to the a similar molecular weight amine, the boiling point increases quite a bit, but not as high as an alcohol. Okay, so bottom line that I'm trying to hammer home, amines, they hydrogen bond, not as great as alcohols. So then because of that, now let's compare primary, secondary, and tertiary amines. Notice how all of these have the same number of carbons, right? So we got the exact same molecular weight in these three compounds here. But primary amines are way better at hydrogen bonding than secondary amines because they just have more donors, right? So I took away one of those possible donors. So notice how the boiling point dropped. And then we get to a tertiary amine that has no donors available for hydrogen bonding. It still has that lone pair, but no sort of hydrogen bond donors. So then the boiling point decreases further. I mean, of course, in terms of nomenclature, when we're talking about uh, having multiple amines there, notice how, again, we include that E-butane butane diamine, because we don't want to have butanedi. You don't want to have those two consonants running together. So you keep the E on there. The other interesting thing why they bring this up is because a lot of these small molecular weight amines have very unpleasant smells. So when you go to a fish market and you're smelling that stinky fish smell, the molecules that are responsible for that are actually amines, right? This is interesting, but not necessarily the focus of organic chemistry, but just something to kind of go back on. Alcohols have that very, we know what alcohol smells like, kind of very like doctor's office-y, hits you right in the face, clears your sinus kind of smells. Amines smell terrible. They smell like rotten stuff, rotten fish. Esters, on the other hand, have those very fruity, pleasant smells. So yeah, just something to keep in mind. Last property of amines we're going to talk about is the basicity of amines and how to compare those. So first of all, we should all be able to do reaction mechanisms for acid-base reactions. Remember, you just have that lone pair on the amine grabbing that proton. This is just a fancy proton transfer that happens. And remember that we can compare the basicity of an amine by looking at the pKa of its conjugate acid, right? So when we're going to talk about comparing basicity of amines. The weaker the conjugate acid, that means the stronger the base. Okay, so in terms of pKa, what makes a strong acid? A low pKa or a high pKa? Remember, low pKa equals strong acid. High pKa is weaker acid. Let's just say weak acid. And so if the conjugate base, if the weaker conjugate acid means that I have a stronger base, that means that a high pKa of that conjugate acid would lead to a stronger base. Okay, so high pKa of a conjugate acid means a stronger base. Okay, so let's take a look at a few sort of like regular old alkylamines here and compare their basicity. First thing I want to point out is just how close all these numbers are, right? So whether you have a small alkyl group or like as is the case of a methyl, or a big bulky alkyl group, as in the case of cyclohexamine, hexylamine, the pKa really doesn't change terribly much, okay? We're going to see things like aromaticity really affect it, but the size of the alkyl group isn't really that big of a deal. Okay, so let's take a look at three kind of closely compared ones. This would be methylamine. This would be just a primary amine with the methyl group. We have dimethylamine. We have a secondary amine with the methyl group. And then we have trimethylamine. Now we have a tertiary amine, all with methyl groups, okay? And so looking at these pKa's, which one is going to be the weakest base? Remember that low pKa is strong acid, high pKa is weak acid, and then importantly, the weaker the conjugate acid, that equals a stronger base. So comparing all these, if I'm looking for the strongest base, I'm looking for the weakest conjugate acid. So then I'm looking for the highest pKa. The strongest base would then actually be the secondary amine here. And the weakest one, right, so this would be strongest. And the weakest one would be the tertiary amine. If we look at another sort of family of very similar ones, ethylamine, diethylamine, and triethylamine, again comparing these pKa's, the highest pKa is the strongest, so that would be the secondary. And the weakest is going to be the lowest, and so that would be the primary. So bottom line is there really aren't any trends that we can use to compare just regular old alkylamines. It's not always as simple as saying that the secondary is the strongest or something like that. We just have to look at the data, look at the pKa's in order to figure that out, okay? And again, the key here being that the higher the pKa of the conjugate acid, the stronger the base, right? Because high pKa means it's a weak acid, and so in turn has a stronger conjugate base. So yeah, so really with regard to this, previous video I said something about trends. Scratch all that. The bottom line is you should just be able to tell by the pKa's, okay? So if you're given pKa data of the conjugate acids, then you can infer something about the strength of the base for these simpler alkylamines. Other times where you might be expected to understand trends is with regard to these heterocyclic amines, and I'll talk about that here in a second, as well as, if I could just skip ahead, what happens when there's an electron donating group or an electron withdrawing group on your amines. Then there should be trends that are predictable without the pKa data. But with regard to these alkylamines, your methylamines, ethylamines, even if there's a big bulky group like an isopropylamine, you really need the data, the pKa data, in order to infer anything about strength. And so then just looking sort of here, if I'm going to go now to these different aniline derivatives, again, let's look at these pKa values and see if we can say anything about what's stronger and weaker. First of all, notice that these are quite a bit lower pKa values for the conjugate acids than when we just had our methylamine or our ethylamine, right? So right off the bat, we can say that these are going to be weaker bases, right? They have lower pKa's, so they're going to be weaker bases. And that's because these all have these benzene rings, and this pair of electrons here is kind of participating in resonance with that ring, so it's not quite as available. Nonetheless, if we're going to look at aniline sort of all by itself, naked, versus when it has a methyl group, versus when it has two methyl groups, we can see that actually the strongest here is going to be the tertiary aniline versus the weakest which is the primary. The last thing to consider with basicity is that the lone pair has to be involved in order for the nitrogen to be a base, okay? So why am I saying, like, what the heck does that even mean? Well, so let's take pyrrole, for example. Notice that the conjugate acid for pyrrole has an incredibly low pKa, which means that pyrrole is a very weak base. It is a crappy base compared to all these other nitrogen compounds we've been talking about. Why is that? Well, if we remember back to our discussion of aromaticity, pyrrole has this lone pair of electrons that's participating in resonance, right? Pyrrole wants to donate that pair of electrons to the ring. It puts it in a p orbital, and it does that because then there are 6 electrons in that ring, all in resonance, which makes it aromatic. Aromatic, remember, is great, right? So that's what makes pyrrole an incredibly weak base, is that pair of electrons is already doing stuff. It's already participating in resonance in order to make it aromatic. If we look at something like pyridine, also an aromatic compound, but the pair of electrons is not participating in resonance. So its pKa is comparable to aniline because it's basically got a lone pair that can act as a base and grab a proton. Okay, so one of the things that we saw with aniline is, we talked about how normal alkylamines have their pKa's of the conjugate acid around 10, 11. Aniline was much lower, right? So it's much weaker of a base. Why is that? Well, remember what aniline does, what the nitrogen in aniline does, is it donates that pair of electrons down to the ring. Right? So not as big of a sort of contributor in terms of resonance as was pyrrole, where that pair of electrons is in a p orbital, so it can participate in the aromatic ring. Here, nonetheless, that pair of electrons is participating in resonance, right? So again, focusing on that lone pair. Is it free to grab a nitrogen or to grab a hydrogen? If so, it's a good base. If it's busy participating in resonance, that's going to decrease the basicity of that nitrogen. And so then that gets interesting for when we start comparing things with electron donating groups, right? So this, if we have this ether group, where did that fall? I mean, this is now going back a few chapters, so I forgive you if you don't necessarily remember off the top of your head. But remember that this is an electron donating group compared to a cyano group or a nitrile, which is electron withdrawing. So even before looking at these pKa's, don't cheat. What do you think is going to make it a stronger base, having an electron donating group or an electron withdrawing group? Remember, it's all about, is that lone pair on the nitrogen, is it free to grab a hydrogen? Well, if there's an electron withdrawing group, that means that that nitrogen wants to donate that pair of electrons to the ring even more, right? Because the ring's electron withdrawing, it's sucking those electrons in there. So that's going to make that nitrogen a much weaker base than if we have an electron donating group. Now, all of a sudden, that pair of electrons isn't as welcome in that ring, right? So the presence of an electron withdrawing group will also decrease the basicity of nitrogen. This is sort of similar phenomena that we see with amides. Again, with nitrogen, what are we thinking when we're thinking basicity? We're thinking, is that lone pair occupied? If it's occupied in resonance, that's going to make it a crappier base. Amides, we know, have this resonance structure, which, although you got split charges here, turns out to be a big deal. Remember, we learned that this bond does not readily rotate because it has that double bond character. So amides are considered not great bases. Okay, and I mean, lastly, we talked about this equation, this Henderson-Hasselbalch equation, a lot in the first semester. We're not going to do any math with it, to be honest, but we could if we really wanted to show that at physiological pHs, which would be, around 7, the ammonium ion is actually what predominates, right? Because the pKa would be around 10, Actually, I guess it's closer to 11 usually. So if the pH is 7, that means that this actually favors the conjugate base. I'm sorry, actually favors the acid, which in this case is the ammonium ion.